Hello everyone. Today I'm going to introduce you to one of the newest concepts in the field of computer vision, YOLO-World, which is a variant of YOLO, or you only look once. This is not just a catchy phrase, but a revolutionary approach to object detection that has transformed how machines see and understand our world. Before we dive into the specifics of YOLO, let's first understand the broader field it belongs to, computer vision. Computer vision is a branch of artificial intelligence that teaches machines to interpret and understand the visual world. By mimicking human visions, computer vision systems can extract, analyze, and comprehend information from images or videos automatically. YOLO is an object detection system that processes images in real time, identifying various objects with a single look. That makes it distinctly fast and efficient and suitable for applications that require immediate and accurate object detections. In comparing YOLO with other models like SSD and faster RCNN, YOLO stands out due to its speed and accuracy. It applies a single neural network to a full image, which allows it to predict multiple objects in every section simultaneously. This approach not only speeds up the process, but also enhances the accuracy by considering the global context of the image. Unlike other models which process parts of the image in isolation, below is a plot that displays the performance of all three models, average precision, and the frames per second it was processed in. Faster RCNN produced a higher precision, 7% higher than YOLO, but at a cost of being 5 times slower. All the models are fairly accurate. YOLO is just faster. It is notable that in this comparison, YOLO's version 3 was used, and version 9 is the most recent version. Object detection models use case extend across various industries. In traffic management, it helps optimize flow and enhance safety. In retail, it analyzes customer behaviors and monitors inventory effectively. In healthcare, it can be used for anomaly detection and autonomous vehicles for obstacle detections. These examples showcase the versatility and wide range impacts on technology and its daily operations. My project focuses on utilizing an object detection model for traffic management at a gas station, which is the very first scenario listed on this page. Monitoring and analyzing traffic can improve customer safety and provide data for optimizing the gas station's operation and layout design strategies. This video displayed is my personal footage of my drone that shows the output of my YOLO model to detect vehicles and track their movement around the area. With just a short video, insight can be gained, for example, which entrance to the gas station is most popular. Despite the strength, YOLO, like all other object detection models, faces several challenges that can affect its performance. I'll outline some of the primary issues and how they impact the field of object detection. First and foremost, data. The requirement for large data sets. Object detection systems learn to identify and locate objects through exposure to numerous examples. This necessitates vast and diverse data sets, which can be costly and time-consuming to compile and annotate. The quality and variety of the data directly influences the accuracy and reliability of the detection. Another significant challenge is managing the trade-off between detection and speed and precision. In real-time applications such as autonomous vehicle driving or public safety monitoring, rapid detection is critical. However, increasing the speed often comes at a cost of reducing the accuracy. Systems must be carefully designed to balance these aspects according to the need of specific applications. Object detection models also require substantial computation resources for training. This process can be prolonged and expensive, particularly when aiming for high precision in a complex visual environment. Furthermore, the training phase must be addressed issues such as variety of object sizes and diverse lighting conditions, which can complicate the learning process. Detecting difficulty objects, such as detecting small or unusual objects, poses another hurdle. Objects that appear infrequently in training data or those that blend into the background can evade detections by even the most advanced systems. Enhancing a model's ability to recognize such objects involves sophisticated techniques and often more specialized training data. When it comes to environment, these operational environments itself can persist a challenge. For an example, conditions such as weather, lightning changes, and crowding scenes and significant impacts the performance of the object detection system. Developing robust models that can adapt to these variations is critical for the reliability of the performance. Addressing these challenges is a key to advancing the capabilities of object detection technology like YOLO. Innovations in datasets, creations, model architecture, and training methodologies continue to push the boundary and enhance both speed and accuracy to meet the evolving demands of real-world applications. Building on the standard YOLO framework, YOLO-World introduces and enhances the address many of the challenges discussed in the previous slide. YOLO-World is designed to overcome these obstacles by requiring no new data for training while maintaining high predictive speeds and accuracy. This was accomplished by using natural language process to describe the images within the training process. The additional embedding allows the model to learn more about the image and not be restricted to only learning from the labels. Using the YOLO-World pre-trained model reduces the technicality and simplifies the model development process. It is not only inherits the strength of the classic YOLO architecture, but also introduces significant and innovations that address many of the traditional challenges in object detection. YOLO-World is a huge step in the evolution of object detection models. In diving through the architecture of YOLO-World, I will highlight its innovative components and how they work together to enhance the object detection capabilities. YOLO-World is built on the foundational YOLO framework, but it incorporates several advanced features to address the limitations of earlier versions and improves the overall performance. YOLO-World introduces the concept of vocabulary embeddings. These features involve embedding a rich vocabulary of object descriptors directly into the model. By doing so, YOLO-World can recognize a broad array of objects more accurately. These embeddings are learned during the training phase and are refined, fine-tuned continuously as the model encounters new objects in different contexts. At the heart of YOLO-World is the YOLO backbone model. This component is responsible for the initial processing of input images. It extracts essential features from the raw image data, which are then passed on to other components for further analysis. The backbone is designed to be highly efficient, ensuring that the feature extraction is both quick and effective, setting the stage for accurate detection. Recognizing objects of various sizes is challenging for traditional models. YOLO-World addresses this through multi-scale image features. This system processes images at different scales simultaneously, allowing the model to detect small, medium, and large objects with equal precision. This scalability is critical for the application like traffic monitoring or retail analytics, where objects of interest vary significantly in sizes. Following the feature extraction, the bounding box head comes into play. This component predicts the bounding box for each detection object. It is used for feature provided by the backbone to determine the location, size, and orientation of each box, ensuring that the objects are accurately localized within the image. The text contrastive head is a unique feature of YOLO-World that enhances the understanding of objects and their textual contents. This component uses natural language processing to compare text description with visual features, ensuring that the model's predictions align with both visual and textual data. This dual input system helps reduce false positive and improves the semantics accuracy of the detections. These image-aware embeddings components further refine the detection process by embedding object-specific and image-specific contextual information. Object embeddings capture the distinct attributes of each object, while image-aware embeddings take into account the overall contextual of the scene, such as a background or inter-object relationship. Lastly, YOLO-World incorporates a vision language pre-trained model network, PAN, a regional text matching algorithm. This component integrates the visual data with the textual information. enabling the model to understand and interpret complex sayings more like a human does. This integration is particularly beneficial for applications requiring detail, scenes, and understanding and categorization. As stated before, YOLO is able to predict multiple objects in every image section simultaneously. It's able to do that by utilizing the grid system. It's able to chop an image into a grid, and each grid cells predicted the bounding box and their confidence score. The bounding box prediction is very similar to a regression problem. It also predicts the confidence score. There are two other components to the object detection. There's the class prediction and non-max suppression. The class prediction uses conditional probabilities of those objects, and the non-max suppression makes sure that the box is as closest to the object as possible, reducing the space. As stated in the other slide, we have about 4 different components that we're trying to optimize. With that being said, we're going to go over the loss functions for this model. These 4 components roll up into one, which is that bottom where it says YOLO loss. Most of these are very similar to regression models. And the first one, defining the bounding box coordinates, those are the coordinates, and you're calculating the variance, squaring it, and you get the number. Then also you're doing the confidence. This is going to be for the non-max suppression to make sure that we're as closest to the bounding box as closest to this object as possible. And then we have a no object confidence. So this kind of helps remove. And the fourth component is the classification. And so those are your typical conditional probability calculations. And you combine those all together to make a weighted loss, and that is the loss function for YOLO. We also need to add one additional component, and that is the tracking part. We first start with the object detection, and then we move into a Kalman filter. The Kalman filter predicts the next position as the object is moving, and then it also checks back at that for the Kalman correction. In between, we'll see the Hungarian algorithm or the bot sort. These are things to optimize the Kalman filter to organize it. All right, so here is the input of the video from YouTube that we're going to be using. You can see that I have it saved as gas station. Then we can go to our Colab code. We're going to quickly run the installs. There's only 4 installs you need, the Ultra Analytics and PyTube. The rest will automatically update if you don't already have those, but that should be done pretty quick. My Colab goes pretty fast. Here are the inputs and all the libraries that we'll be using in this code. And PyTube did have an error that I had to figure out it for the last 2 days ago before everything was due. It stopped working. YouTube changed their code. So this is the fix. You just got to make sure that you refresh the directory in Colab, as you see now, and then you put your URL that you want to create tracking with, and then here you just execute and it gets the path and it takes that URL. If you wanted to preview any of the YouTube videos before doing your object tracking detection, you can use this display function that I've created, and then we have our counter tracker, which keeps count of unique counts of the objects that we are tracking in our video. This video prediction is the actual model that is predicting with YOLO-World. And then to execute it, we can either use a path if we want to drop it in. If we don't want to use a YouTube video, you can just drag and drop. And then right here is our object parameters. Then we can just go ahead and run that. Right now, it is using YOLO-World. And then it's going to actually create a second model, and that second model is customized based on the prompt that you put in there, such as you can put car or you can put roof of car. If you want to track the wheels of a car, you literally just use natural language to type it in there and it'll classify that. You can put several, you can classify more than one object, and you do not need to train. So at this time, you see where it states processing video frames. This is actually predicting on each frame. You can see that we have a predicted download file, and that's the file that we're going to be viewing. And then we just And so the file is downloading on your personal desktop. If you have some other way of playing it, you could just write a code to do that. As you can see here, we are tracking each of the vehicles. The first ones that appear, this is a drone shot, so the closer the vehicle is to the drone, it seems to be classifying it better. But this application allows us to see what what entrance to the gas station is getting more traffic, and you can listed in the documentation. You can see other strategic advantages of using this application. Just wanted to say thank you for watching and listening, and thank you.